Hello, welcome to Engineer's Mindset. Now let's consider the problem on the board. It says, analyze the truss system shown and determine the forces in each member using joint method. Okay, so as always, first thing to do is to outline the free body diagram. So we have FBD. It's not much of a big deal, just remember the beam or the truss the way it is. Okay, and then identify the hidden forces by the supports. So we have this. Now at point A we have the pin supports, and for a pin support we have two reactions, one vertical and one horizontal. So we'll simply have call this simply RAY, and then one horizontal simply RAX. This is joint A. Okay, and joint B and joint C, at joint C we have a roller, and for a roller we simply have a single support, okay, which is this. So this is simply RC, a support normal to the surface. This is joint C. Okay, so we simply connect our joint B, connect to joint P, and this is joint B. Okay, so we have this. Okay, so this is actually a square truss system. This is B, and this is E, with equal sides. Here is 4, here is 4. So which means from A to B is actually was 2 meters, and from B to C is also 2 meters, because it's actually a square truss system. Now at point D we have a force of 20 kilonewtons acting downwards. So there is a point code here, 20 kilonewtons acting at joint D. At joint E, there is also a force of 10 kilonewtons. So at joint E, we have a point load of 10 kilonewtons acting there. Okay? So you have this. So that's your free body diagram. Next is to employ the equilibrium law to find these reactions. So we employ the equilibrium law from the static equilibrium law. Equilibrium law. Okay, we simply have that summation of force in the x-axis is equal to 0. Okay, so we're simply going to have the only force pointing in the x direction here is simply RAX. So that simply means that RAX is equal to 0. So that one is off. Next, summation of vertical force equals 0. Let's consider vertically upward force as positive, vertically downward force as negative. So we simply have RAY pointing upwards, so it's positive. We have RAY. We also have RCY pointing upwards, so it's positive, plus RCY. We also have 10 kilonewtons force acting downwards, so it's negative. We have minus 10 kilonewtons. We also have 20 kilonewtons force acting downwards, so it's negative. Simply minus 20, and this is equal to 0. Okay, so RAY plus RCY minus 10 minus 20 simply gives us minus 30. Okay, this gives us minus 30. Minus 30 equals 0. So let's simply say minus 30 over this equation. We have RAY plus RCY to be equal to negative sign plus and equal to sign becomes positive. So we simply have 30. Call this equation 1. So at this point we have two unknowns in one equation, which is very impossible to solve. But the only possibility is by taking another equilibrium law, which is take moment about a point on the system. So we simply consider taking moment about a point. And I said, if you're taking moment, take moment about the point where we have numerous of force on the system. So notice that at point A we have two reactions or two unknown forces. So take moment about that point so that the effect of this force about that point becomes 0. So taking moment at point A, take moment at point A. Okay, summation of the moment at A equals 0. Let's consider clockwise to be positive, anti-clockwise to be negative. So you have this. Okay. Now, the moment of this 10 kilonewtons force about point A automatically becomes 0. I've always said that moment is actually the product of force and the line of action of the force to the point which is perpendicular or distance perpendicular to the point of moment. So the line of action of the force and the distance must be at 90 degrees. So I already said that if a force lies on the same plane as the position or the plane of the distance, then the moment of that force about that point is 0. This force, currently this force, is on the same plane as the distance of moment. They are on the same plane, no angle between them. So since that force lies on the same plane at the point of moment, the moment of that force about that point automatically becomes 0. Okay. Next now is to find the moment of this force, 20 kN force about point A. And the line of action of this force is actually this, coming downwards. This time that means an angle of 30 degrees to point A simply from here to this point is 2 plus 2, and that's 4 meters. So the moment of this force about point A is simply for this force 20 times total distance takes to point A, and that's 4 meters. Also, since this force is acting downwards, it turns about in this direction, which is positive to our direction, so it's clockwise movement. So the moment of that force about that force simply becomes 20 times 4. Also, the moment of this force, RCY, about point A, the force is pointing upwards. So if you turn in this direction, so it goes in this direction to point A, which is anti-clockwise and stability. Distance, it takes this force to point A is simply 2 plus 2, and that's 4 meters. So the moment of that force about point A is simply minus RCY times 4, and this is equal to 0. Okay, so 20 times 4 is 80 minus 4 RCY equals 0. So less than minus 4 RCY over here. Negative side plus that equals and become positive. I will simply have 80 equals 4 RCY. So to make RCY subject, divide both sides by 4. That's simply implies that RCY is simply 80 divided by 4. Therefore, RCY is simply 20 kilonewtons. So if I have RCY of 20 kilonewtons, simply substitute the value into equation 1 to find RAY. Okay? Alright, so from equation 1, I simply have RAY plus, in place of RCY now, simply put in 20. Okay, and that's equal to 30 kilonewtons. So simply now send plus 20 over to this side of the equation. Positive sign plus and equal sign becomes negative. You simply have RAY to be equal to 30 minus 20. And that simply implies that RAY is equal to 10 kilonewtons. So having known the reactions now, we can now substitute the reactions into the free body diagram. Okay? So RAY is 0, so this one is up. And we obtain RAY simply as 10 kilonewtons. So we simply have that to be 10 kilonewtons. We also obtain RCY to be 20 kilonewtons. So this is simply 20 kilonewtons. So we can now start the joint method. And I said, if you want to start the cross analysis, using joint method, go to the joints that have least amount of members, because the number of members in each joint determines the number of unknown. So if I move at joint A, I have just 2 members from A to B and then from A to B. So which means normally I have just 2 unknowns. But if I move to joint B, I have from B to A, B to C, B to E, B to D, and B to E, which is about 1, 2, 3, 4 unknowns. So start with joints that has least amount of members. So let's consider joint A. Consider joint A. Now at joint A we simply have this and this. Is all we have at joint A. Then we'll have the 10 kilonewtons for pointing upward. So we simply have a reaction here, 10 kilonewtons. This is joint A. Okay. Now I said each member of the cross system carries 2 equal but opposite forces. Now we don't know the direction of this force. So let's now assume between A to E, let's assume that the force is tension. So it's going out of the joint. So we simply assume a tensile force. Also between A to B, let's also assume tensile. So the force is going out. Tensile. Okay, so this is simply force at joint A relative to point E, force adjoint A relating to E, while this is force adjoint A relating to what? Joint B. We have this force already in one dimension, so they are not defined. Okay? So we employ simply our equilibrium law. From equilibrium law, summation f of x equals 0. So that simply means the forces in the x direction, sum them up and equal them to 0. The only force pointing in the x direction is simply what? FAB. So that simply means like that FAB is equal to 0. Also, solution f of y equals 0. Considering vertically upward as positive, vertically downward as negative. Okay? So we sum all the vertical upward forces and equate them to 0. So we have 10 kilonewtons pointing upwards is positive. This is 10. We also have FAE pointing upwards, so it's positive, plus FAE. And this is equal to 0. Okay? So to make FAE subject, simply send plus 10 over to this side of the equation. We're going to have. Okay, so FAE is now equal to minus 10 kilonewtons. So we assume tension for the force at joint A related to E, and then we are obtaining negative sign. It actually means the direction we assume was wrong. So it means the original direction of this force is also the what? Compression. So therefore, FAE is simply 10 kilonewtons C for compression. Okay, which shows that the force at that joint is actually compression and not tension. Alright, so we are done with that joint. Next, let's consider joint E. Since we now move from A to A, the same as from A to E, so we can consider joint E looking forward the force in members ED and members EB. So considering joint E, let's see what we have at joint E. Considering joint E, so at joint E we simply have this, and this. Then we have a 10 kilonewtons force acting downwards there, 10 kilonewtons at joint E. Okay, so the force from joint E down to joint D. Let's also assume tension. Once we don't know the direction of the force, so let's assume tension to assume that this force is actually going out. So this is simply F, the force at joint E relative to point D. Same thing happens from joint E to point B. We don't know the force. Let's also assume tension. Okay, so let's assume that the force is tensile. So this is force at joint E relative to point B. Okay, already the force at joint A relative to point E was given to us as compressive force. We've got negative, so it means it's supposed to be a compressive force and not tensile. So it means now at joint D we are going to put it in the real direction of that force, because FAE is equal to FEA. So therefore, the force at joint D relative to A is actually what? Compressive, so it has to be going into the joint, and the value simply remains 10 kilonewtons. So FEA is equal to 10 kilonewtons. So you have this. Now, if you draw this imaginary line, okay, it means now that this force is inclined, FEB is inclined to an angle, either to the horizontal or to the vertical. So we need to find this angle, okay? To do that, simply, we know that to be 2 meters, we need this angle theta. Let's call this angle theta. This is 2 meters and this is 4 meters. The adjacent side is 4 meters. So we employ our trigonometric analysis. Tan theta is simply opposite all over adjacent. Okay. Alright, so knowing that this is 2 and this is 4, we can employ the identity. Tan theta is simply opposite. Opposite is 2 meters all over adjacent. Adjacent is 4. Okay, so which means tan theta is actually 0.5, and therefore theta itself is simply tan inverse of 0.5. So which means the angle which that force is actually inclined is the tan inverse of 0.5.
26.565.
What?
26.565.
So approximately 27 degrees. So this angle is 27 degrees. So it means that the angle of inclination here is actually 27 degrees. So if here is 27 degrees, it means this angle there is simply 63 degrees. So we can now resolve this force towards vertical and horizontal. If we take resolving this force to the vertical simply means hold the tip of the arrow of force, put the force in the vertical line. If it passes through this angle, then multiply by the cos of the angle it passes through. But if you put this force now to meet the vertical line, notice the direction of this force. This force points downwards and it passes through this angle to be 7 degrees. So it simply means FEB cos 27 multiplied by the cosine of the angle it passes through. Also, if I resolve this force to the horizontal component, hold the tip of the arrow, pull the force to meet the x line, observe the direction of the arrow. If I pull this force to meet the x line, the arrow still points to the right. So I'll have this force pointing to the right. Okay, and it passes towards 63 degrees. So that means I'm going to multiply this force by cosine of the angle it passes through. I will simply have FEB cos 63. So I have this. So I'll be able to resolve this force now in one dimension, x and then y. So we can now employ a equilibrium law to solve. The first equilibrium law, summation of force in the x-axis equals 0. So we put all the forces in the x-axis and equate them to 0. First we have FEB pointing to the right, so it's positive. We take it out FEB. Next we have FEB cos 63 pointing to the right, so it's positive. So we have plus FEB cos 63. There is no other horizontal force, so the whole of this is equal to 0. Okay? Alright, so we simply have FEB, okay, plus cos 63 is what? Cos 63.
0.4539.
Okay, so cos 63 is simply 0.4539 FEB, and this is equal to 0. So let me send 0.4539 FEB over to this side of the equation. I will simply have FEB to be equal to, this will give me minus 0.4539 FEB. Call this equation 1 at point C. Next, we can put the second equilibrium law, summation of force in the y-axis is equal to 0. Let's consider vertically upward force as positive, vertically downward force as negative. If we do that, okay, at joint E we have 10 kN force acting downward, so it's negative. So you simply have minus 10. We also have FEB cos 27 pointing downward, so it's negative. Minus FEB cos 27, and this is equal to 0. So let's simply send minus FEB cos 27 over to this side of the equation. We are left with minus 10 here, and that's equal to negative sign, constant equal to sign becomes positive. You simply have FEB cos 27. So to make FEB subject, divide both sides by cos 27. That simply implies that FEB is equal to minus 10 all over cos 27. Okay, and therefore FEB. Okay, so minus 10 divides
Minus 11.223.
minus 11.2 kilonewtons. So assumed for FEB, we assume tension and we are having negative sign. So it doesn't mean we are wrong, it only means that the direction we assume is actually wrong. So which means FEB is actually supposed to be what? Compressive. Should be going inwards instead of going outwards. So we now introduce that into the answer. FEB is now equal to 11.2 kilonewtons, simply compressive C. So that gives us the force at joint E relative to point B. Okay. Next is to find substitute this value into equation 1 to find the value of FEB. Okay, so from equation 1 we have that FEB the force adjoint A relative to D is equal to minus 0.43539. Then in place of FEB, we'll simply put in 11 point minus 11.2, please don't forget. Simply put in minus 11.2. So therefore FEB is now equal to minus 0.4539 times minus 11.2. This gives you 5.08 kilonewtons. Okay? So we assume tension and we also obtain tension. We said let the force from joint A relative to D be pulling out. We assume tension and also obtain tension positive. So it means the direction assumed was correct. So that becomes the force at joint E relative to point B. Sorry, that becomes the force at joint E relative to point B. Okay, joint E relative to joint B. Alright, so we have that. Okay, so we've gotten the force at joint A relative to E. We've gotten the force at A relative to B. We've obtained force at E relative to D. Now let's consider joint C. You can consider joint C, or you can still consider joint D. Since you already know this force, it means we just have two unknowns here, D to B and then D to C. Or you can still consider joint C, since we have two unknowns here, so C to D and then C to B. You can consider joint C or any of the joints between C and D to solve. Let's consider joint C and C. Okay, so let me pull out this value, FED, to be 5.08 kilonewtons. Let me give you somewhere here. FED, we obtain 5.08 kilonewton tension. So we obtain that. Let's see from here. Okay. I think that's all for now. Let's also keep FED 11.2 kilonewtons compressive. FED equals 11.25 kilonewtons compressive. FAE 10 kilonewtons compressive. FAE equals 10 kilonewtons compressive and FAB equals 0. Alright, we can wipe this point now. Alright, so consider joint C. Okay, so what we have at joint C is simply we have this, we have this. Okay, this is joint C, and then at joint C we have an upward force RCY, whose value is simply 20 kilonewtons. Okay. Now we don't know the force between the direction of the force between C to B. We also know the direction of the force between C to D. So we assume those directions. Okay, let's assume tension that the forces are pulling out of the joint. Okay, or you can also assume compression, whichever way. Let's assume that from C to B is tension, so it's pulling out of the joint. So this is force at joint C relative to joint B. Let's now assume C to D to be compressive, that the force at joint C relative to joint B is compressive. So we'll simply have FCD. Let's assume compressive for FCD. Okay, so all we need to do is simply what? Since the forces are one dimensional, this is purely on the x axis and this is purely on the y axis. So we simply will employ equilibrium law. From equilibrium law, we know summation f of x is equal to 0. So sum of the force in the x axis and equate them to 0. The only force pointing in the x direction here is what? FCD. And of course, it points negative, it doesn't matter. Minus FCD is equal to 0. So it simply means that FCD itself is equal to 0. Alright, so please take note, since the beam is symmetrical, that this is a square beam, it means the reaction we obtain from A to B must be equal to the reaction we obtain from B to C. That's why having FCD to be 0 and FAB also being as 0. Next is to employ the second equilibrium law. Summation of vertical force, summation f of y to be equal to 0. So we consider upward force as positive, downward force as negative. Okay, so we have 20 kilonewtons pointing upwards, positive. So we have 20. We also said let FCD. Okay, FCD is coming down, so it's negative. Minus FCD, and that's equal to 0. Okay, so if we send FCD over here, minus FCD over here, negative sign plus sign equal sign becomes positive. So I'll simply have FCD to be equal to 20 kilonewtons. Alright, so I assume compression for FCD, like I assume that the force should be coming into the beam, that's compression, and I obtain a positive value, so which means the direction assumed was actually correct. So FCD is actually what's under compression. So it becomes FCD compression. So that's the force for FCD. Okay? Okay, so having known that, let's put them up. FCD, let's put this value here. FCD give us 0, and FCD give us 20 kilonewtons compressed. Alright. So finally, we've known all the reactions in each of these joints. We know E to B, so automatically we know B to E. Okay, we know A to B, we know B to A, we know B to C, we know C to B. So we are left with what? D to B, unknown. Since we know ED and we know CD, we can now pick joint B to find the reaction at joint D to B. So let's consider joint B. Consider joint B. Consider joint D. At joint D, we simply have this, and this. Okay? We have something like this. Okay, so this is joint D. We also have 20 kilonewtons force acting now there. 20 kilonewtons joint D. Okay. And so we said we obtained that the force from C to D is 20 kilonewtons compressing. So which means this force is actually going into the joint C. So that also means, since I said a truss system carries two equal but opposite forces each at the joint, it also means that from D, the force that points from D to C also has to go inwards into the joint. So you have to have this force going into the joint of D. So you have to be compressing, and the value is still same. FBC is equal to FCD, and it remains 20 kilonewtons. Since we obtain FCD as compressive, it means we have to reflect it here. This is joint C. So it also has to be compressed entering into the joint of D. So this is the F at joint B to C, and it remains 20 kilonewtons. Okay, next we obtain FED. FED was obtained as 55.08 kilonewtons tension. So it means it was pulling out of the joint. So it also has to pull out of the joint there. So this is simply force at joint D related to E. So it still remains 5.08 kilonewtons. So the only force we don't know now is the direction of D to B. So let's assume tension for D to B. If we assume tension, okay, simply putting out this force at joint D relative to B. Now look at this force is actually inclined to an angle. Okay, to the vertical and to the horizontal. So let's find this angle and see. Okay. So this is the angle to the vertical, it's called theta. And this is same thing as saying, since you know the adjacent side and we know the opposite side, it's opposite to all over 4. So it still gives us the same angle as for 27 degrees. So the angle of this force to the vertical is 27 degrees. So we simply have here 27 degrees. And if here is 27 degrees, it means here is obviously 63 degrees. So all we need to do now is resolve this force into what? Vertical and horizontal component. Resolving this force with vertical component, hold the tip of the arrow of the force, pull it in this vertical line. This is the vertical line. Now, if it passes through the angle, multiply by the cosine of the angle it passes through. And also observe the direction of the arrow. If I pull this force to the vertical line, this force points downwards. And it passes through this angle 27 degrees. So the value simply becomes F dB cos 27 If I pull this force, if I resolve this force to the x axis, pull it forward, I will pull it away the x line. Notice that this force will be pointing to the left. So you have this force pointing to the left in the x direction. Also, it passes through this angle 63 degrees to get the polar coordinates. So simply multiply by cos. Okay, so we have FDB cos 63. Cos 63 degrees. Okay, so that's all. Having known this now, we can employ any of the equilibrium equation can go to give us the answer. So let's pick because the other directions are known. So we'll start from our equilibrium equation summation f of x equals 0. So we sum all the force in the x axis and equal to 0. We have f dB cos pointing to the left, so it's negative, minus f dB cos 63. We also have f dB pointing to the left, so it's negative, but f dB has a value, and the value is 5.08. So we simply have minus 5.08. Okay, those are all the forces we have in the left axis. So this is equal to 0. So I can now send minus 5.08 over to this side of the equation. Negative sign plus and equal sign become positive. I will simply have minus f dB cos 63 is now equal to 5.08. So to make f dB subject, simply divide both sides by what? Minus cos 63. Okay. So I'll simply have FDB to be equal to 5.08 divided by minus cos 63. Okay, so this is equal to 5.08 divided by
11.1896
minus 11.19 kilo newtons. Okay, now we assumed tensile for FDB and we're having negative value. So it means the original direction is supposed to be compression. So therefore the force in just D related to B is actually 11.19 kilonewtons compressive. Alright guys, so that is the final force acting on the system. Okay, so I hope you find the video interesting. Please, if you're new to the channel, don't forget to hit the subscribe button to get more and more content like this. And of course, I would like to get your thoughts in the comment section. I will see you in the next video with more questions on joint method of Truss analysis. Thanks and cheers.